Welcome to day 37 of the 42-day STL Mastery series. In this session, we are diving into one of the most exciting and practical uses of STL, competitive programming. Competitive programming requires speed, accuracy, and an efficient approach to problem solving. And today we will focus on how the standard template library can give us a significant edge in coding competitions. From optimizing our code's performance to reducing the amount of boilerplate code, STL is indispensable in the world of programming contexts. Let's get started by exploring why STL is crucial in SCP. Competitive programming is all about solving problems under strict time constraints, often with large input sizes. This means every second counts and we need to work smarter and not harder. STL is a powerful tool in this context because it provides us with pre-built data structures and algorithms that are both efficient and optimized. By using STL, we can avoid having to write complex data structures from scratch. For example, containers like vector, map, and set are implemented with optimal time complexities. This not only saves time but also ensures our solutions are robust and run within time limits. Plus, STL's optimized algorithms such as sort, binary search, and accumulate are tested and efficient, allowing us to solve problems in a fraction of the time compared to writing our own algorithms from scratch. In competitive programming, we will work with a set of key containers that should be part of our toolkit. This includes vectors, sets, maps, unordered maps, priority queues. Let's break them down. Vectors are used for dynamic arrays that can grow or shrink in size, perfect when we don't know how many elements we need at the start. Sets and unordered sets are unordered collections with no duplicates, while unordered sets provide faster access via hashing, especially useful for problems requiring fast memberships. Maps store key value pairs and unordered maps are optimized for fast access, making them perfect for problems involving associative data. Priority queues. These are special queues where the largest or smallest element is always at the front. They are essential for problems requiring greedy algorithms or scheduling tasks. DQ, a double-ended queue that allows you to add or remove elements from both ends efficiently. These containers allow us to write faster, more efficient code while handling a variety of problem-solving scenarios. Now let's talk about STL algorithms, which are just as important as the containers. STL offers a wide array of algorithms that help us solve problems quickly and efficiently. Sorting, the sort function, is a common tool in many competitive programming problems. It's implemented using an efficient algorithm, typically intro sort, which has a time complexity of n log n. Binary search. Algorithms like binary search, lower bound, and upper bound help us search through sorted data in logarithmic time. This is crucial when dealing with large data sets. Accumulate and iota. Accumulate sums up elements in a range, and iota initializes a range with sequential values. These algorithms are incredibly useful when you need to perform operations on ranges efficiently. Next or previous permutation. These algorithms help us generate all possible permutations of a set, which is essential in combinatorial problems. These built-in algorithms not only simplify our code but also ensure that our solution is as efficient as possible. STL isn't just about knowing the containers and algorithms, it's about using them smartly. There are several STL tricks and idioms that will help us solve problems more efficiently and with cleaner code. Emplace back versus pushback. Emplace back constructs an element in place which can be faster than pushback, which requires copying or moving the element. Erase remove idiom. This is a powerful technique used to remove elements from a container. Instead of looping through and manually deleting elements, the erase remove idiom lets us remove elements in a single line of code. Custom comparators. STL allows us to use custom comparators when sorting containers. This is incredibly useful when we need to sort data in a specific order. Count if any of all of. These algorithms allow us to check conditions on ranges of data in a very readable way. They can help us avoid writing custom loops and make our code more declarative. These tricks will save our time, and make our code more efficient and readable. Fast input and output handling can significantly impact the performance of our solution, especially in problems that involve large amounts of data. By default, C++ streams like cin and cout are synchronized with C's stdio, which can slow down input-output operations. To speed up things, we can disable synchronization with iOS ::sync underscore with stdio false, and untie cin from cout with cin.tie null. This ensures that I/O operations are faster and we can handle large datasets more effectively. In situations where performance is even more critical, using scanf and printf may offer an additional speed boost. Just remember that efficient I/O is often the difference between passing and failing time limits in competitive programming contexts. Let's look at a problem we might encounter on platforms like Codeforces, finding the number of pairs ij such that I is less than j and ai plus aj modulo k equals to 0. This is a classic problem that can be solved efficiently with STL. The brute force approach would involve checking all pairs, which is slow for large inputs. Instead, we can use an unordered map to store the remainders of the elements. For each element, we calculate the remainder and check how many previous elements have complementary remainders to form a divisible sum. This reduces the time complexity from n squared to n, which is a huge improvement. Here's another problem: finding the maximum element in each sliding window of size k. A brute force approach would be to iterate over every window and find the maximum in each, which would take n times k time. However, we can solve this problem in n time by using a dequeue. We maintain a dequeue of indices of the elements in the current window. The dequeue is kept in decreasing order, so the front of the dequeue always holds the maximum element for the current window. When the window slides, we efficiently update the dequeue by removing elements that are no longer in the window and adding the new element. Now let's discuss some STL best practices for competitive programming. First, always be aware of the time complexity of operations for each container. For example, inserting into a vector in constant on average, but inserting into a set is log n. Predefine templates for common patterns like binary search or sliding window problems to save time during contests. Also, avoid unnecessary copies of large containers, as this can degrade performance. Instead, pass containers by reference whenever possible. Finally, custom comparators are a powerful tool for sorting, and handling edge cases properly is crucial in any solution. Now that we have learned the theory, it's time to practice. Here are a few competitive programming challenges to apply your STL knowledge. LeetCode's top k frequent elements, Codeforces, Poshmark and flowers, at Odar's ABC's sliding puzzle. These problems require efficient use of STL containers like unordered map, set, and vector. Try solving them using only STL to reinforce what you have learned today. As you practice, focus on how STL reduces the complexity of our solutions and speeds up our problem-solving process. That brings us to the end of today's lesson. We have learned how STL containers and algorithms can be a game changer in competitive programming. We discussed STL's role in simplifying problem solving, speeding up coding, and optimizing performance. In the next session, we will explore how to apply these skills in real-world competitive programming platforms like LeetCode and Codeforces. Keep practicing and you will soon find yourself solving problems faster and more efficiently than ever before. Great job today, and I will see you in the next session.